Welcome to this video. This is a part 1 playlist for Electrochemistry grade 12. We use batteries in our everyday lives. For example, the battery in your cell phone is called a lithium-ion battery. The battery in your car is a lead-acid battery, and your watches will use a silver oxide batteries. Some batteries are rechargeable, while some we throw them away after we use them. A battery consists of multiple electrochemical cells, and within each cell there are electrochemical reactions. These electrochemical reactions involve a transfer of electrons, and there is a conversion of chemical potential energy to electrical potential energy and vice versa. Electrochemical reactions happen through redox reactions, which are defined by oxidation numbers. We call oxidation number of an element in a compound as a number that shows you how much electron rich an atom is. It shows you how electrons have moved during the interactions. In this video, we are going to discuss two types of electrochemical cells. One is called a galvanic or voltaic cell, which is defined as a cell in which chemical energy is converted to electrical energy through a spontaneous chemical reaction. Two beakers, and we're going to insert these two metals connected to a voltmeter, and we're going to insert this. So let's name each and every component. We call the metal plates electrodes. We call the liquid or the aqueous solution an electrolyte. Voltmeter, which is connected across the external circuit. And we call this U-shaped tube a salt bridge, which has a porous material like a cotton wool inserted at the ends of the two sides. We'll look at an in-depth analysis of what this setup do when we dive deep into galvanic cells. The second electrochemical cell we'll discuss is called an electrolytic cell, which is defined as a cell in which electrical energy is converted to chemical energy. And in these cells, reactions are non-spontaneous. These cells will make use of one beaker with an electrolyte, and will have two electrodes inside. For the cell to run, we need a DC battery connected to each electrode. We will look at an in-depth analysis of the electrochemical cells. Let's revise the oxidation and reduction reactions, also called redox reactions. Oxidation is defined as the loss of electrons. When a substance is oxidized, we call it a reducing agent because it donates its electrons to another reactant. Oxidation is associated with an increase in oxidation number, which we'll look at the rules of later on. Let's look at an example. If we look at the oxidation number on the reactant side, the oxidation number of zinc is 0, but on the product side, the oxidation number of zinc is +2. So we see an increase in oxidation number. Then we call this half reaction a oxidation half reaction. We say an anode is the electrode where oxidation takes place. Reduction is an exact vice versa of oxidation. It is defined as the gain of electrons. If a substance is reduced, we call it the oxidizing agent, which means it accepts electrons from another reactant. Reduction is associated with a decrease in oxidation number. Let's look at this half reaction involving copper. Copper starts with a charge of +2, and at the end it ends up with a charge of 0. So we can see a clear decrease in oxidation number. We define a cathode as the electrode where reduction takes place. Let's look at a couple of helpful mnemonics to help us remember these concepts. We have oil rig, which stands for oxidation is loss, so that is the oil part, and the rig part stands for reduction is gain. The second one, in the context of oxidation, we say an ox, which means anode is where oxidation takes place, and a red cat, which means reduction takes place at the cathode. So when you have these three, you basically have the chapter on your fingertips. Let's talk about oxidation numbers. Oxidation number is defined as the charge or the probable charge that an atom of an element in a compound will have if electron transfer is considered to occur in all bonding, including covalent bonding. Here we'll discuss the rules of assigning oxidation numbers. These were done in grade 11, so I won't go into much details on them. I'll only discuss a few which are going to be very important in this chapter. The first one says the oxidation number of an atom in an unbonded element is 0. If it is a pure element, then the oxidation number, if there's nothing there, it means it is 0. So we say the oxidation number for that is 0. The oxidation number of simple monoatomic ions is equal to the ionic charge. For example, if you look at group 1 metals like potassium, they have a charge of +1, so we say the oxidation number is +1. If it is group 2 metals, the oxidation number is +2, for example, calcium 2+. In the allocation of oxidation number, the charge is conserved, which means the sum of the oxidation number of atoms in a compound must add up to 0 in neutral compounds. For example, a compound like copper sulfate doesn't have any charge. We say the oxidation number of the whole molecule is 0. And the oxidation number must add up to the ionic charge in polyatomic ions. For example, if you have an ion of SO4 2-, the oxidation number must add up to -2. Remember, more electronegative elements will usually get a negative oxidation number, so they will dominate. Just make sure you pause the video and understand all the rules. I'll make a separate video on balancing redox reactions under acidic medium. In the next video, we will discuss redox reactions in galvanic cells. Cheers.